Today, we will show you how we designed and optimized a compressed air water rocket system to maximize the flight time of our payload, an egg. The mission requirements are as follows. The egg cannot be damaged during the flight. All parts of the rocket must stay attached during flight. The design must be reliable enough to operate in a range of favorable weather conditions. And the rocket must pass the standard safety inspection before launch. It may sound complicated, but not to worry. After all, it's not rocket science. Wait.
The pressurized air stores the potential energy and pushes on the water in the bottle. This pushing force expels the water out of the nozzle at a high velocity. Following Newton's third law, an equal and opposite force is produced, causing the rocket to accelerate upwards. Water fraction is the ratio of the volume of water to the volume of air in the rocket. Changing the water fraction changes the mass of the rocket and the total impulse that can be produced. The simulation in the top left is a low water fraction and therefore not enough reactive mass to produce a sufficient impulse for a longer flight. The simulation in the bottom right has a high water fraction. In this case, the increasing mass of the rocket outweighs the increase in impulse, resulting in a short flight time. A water fraction of 0.53 projected the longest flight time for our rocket.
Fins keep a rocket steady so they remain nose up in launch. This allows the rocket to travel further into the air. However, fins must not be too large in order to reduce the effects of drag on the rocket. The features that go into fins include fin area, fin aspect ratio, fin sweep angle, and hub vertical offset. To test all these features, Unity was used to simulate the rocket launch. Some rocket design, launch settings, and wing conditions were kept constant, and then each feature was tested in order to find the perfect fins for our rocket design.
Terminal velocity is achieved when the upward force of air resistance becomes equal to the downward force of weight. Therefore, increasing the parachute area increases the drag acting on it and decreases the terminal velocity of the rocket. For a longer flight time, the area of the parachute must be large. Therefore, the chosen diameter of 1 meter is the best fit in meeting the mission objective of maximizing flight time.
Fins were set at an angle of 15 degrees from horizontal to provide the needed stability but also to allow for greater speed. The area of each of the 4 fins is 0.01 meter square to again provide stability but also small enough to limit weight and drag. We were careful to not have the water volume fraction too large so that the increased mass of water would outweigh the positive of the greater impulse. The areas of the parachute was found to be optimal at 1 meter diameter. This was because the larger the area means a larger drag and a lower terminal velocity.
Real-world considerations. The main consideration is wind when considering operating weather conditions. When launching a rocket with such a light dry mass, a crosswind can have considerable effects on the flight path and therefore flight time of the rocket. As seen in this image, a crosswind of velocity W against a rocket with an upwards velocity R will cause a resultant force on the rocket downwind. This flight path will result in a lower flight time. However, if acceleration and the polar moment of inertia is adequately large enough, the rocket will be less affected by the crosswind. In that respect, the team made it a priority to ensure the initial thrust of the rocket was high enough to cause a large enough acceleration to combat the crosswind. We decided our bottle should be a fizzy drink bottle due to the fact they are made from PET, which is an enormously strong plastic, and therefore better suited to the high pressures the rocket will experience. The fins are to be made from deep-run foam, which does not split easily and is lightweight. Also, it's a consistent weight and density, which is crucial for our project in maintaining the balance of the rocket.
To conclude, these are some of the things we've learned so far. Delegation only works with proper communication. Frequent follow-up is key to keeping an engineering team on the same page. Theory can only take you so far. One should delegate effort into considering every possible factor when solving an engineering problem. Finally, modern engineering tools like CAD and simulation software streamline the design process exponentially. Being proficient in their use can make all the difference towards good design.